After weeks and weeks of learning about various nuanced parts of calculus, including vectors, vector valued functions, parametric functions, power series, and probably a couple other topics that I've forgotten at the moment, we're going to now dive into what we traditionally call multivariable calculus, beginning with functions of several variables. Functions of several variables. So far, we've dealt with the calculus of functions of a single variable. But in the real world, physical quantities often depend on two or more variables. So now we turn our attention to functions of several variables. Functions of two or more variables and their domains. A function of two or more variables is a rule that assigns a real number to every point in its domain. So the domain is a subset of Rn, and the range is a subset of R. There are many familiar formulas that depend on two or more variables. For example, the area of a triangle, A equals 1/2 base times height. The two variables are base and height, and the dependent variable is the area. The volume of a box, V equals L times W times H. Here, the independent variables are L, W, and H. There's three of them. And the dependent variable, V, is the volume. Or the average of a list of n values, x bar equal to x1 plus x2 plus ... plus xn, all divided by n. Here, x bar has n independent variables, x1, x2, all the way to xn, and the dependent variable is x bar. We use the following notation. Y equals f of x gives us functions of one variable, the variable x. Z equals f of xy would give us z as a function of two variables, x and y. W is equal to f of xyz would be a function of three independent variables, x, y, and z. We could continue on in this manner all the way to u, or whatever letter seems to float your boat. In this case, u equals f of x1, x2, xn. Here, there are n independent variables, x1 through xn. Most of our time is going to be spent on functions of two variables. So definition. A function f of two variables is a rule that assigns to each ordered pair of real numbers, x, y, in a set D, a unique real number denoted by f of xy. The set D is the domain of f, and its range is the set of all values that f takes on, that is, the set of all f of xy's such that xy is in the domain D. The domain. If a function is given by a formula and no domain is specified, then the domain is the set of all points for which the given expression is a well-defined real number. So there be no zero in the denominator, no negative under the radical if there's an even index, no zero or negative when taking logs, etc., etc., etc. So for functions of two variables, one way of visualizing such a function is by means of an arrow diagram, where the domain D is represented as a subset of the xy plane. So here, your D is the kind of bean-shaped region, and there would be points, x, y in that region that will map to various z values. Different x, y, different z. Notice that it's okay if there's more than one. It's okay if there's more than one point xy that goes to the same output z. What's bad, what's illegal, is having one point mapped to two different values. This would be bad. This would mean not a function. Okay, so this is just kind of the caution. Let's look at a manipulate to better understand what's going on here. In this picture, notice that on the ground floor, if you will, that'd be this region here. we have our domain. Right, here's our domain. Okay, and up above here, we have our surface. It wouldn't have to be above, it wouldn't have to be a nice surface, but certainly makes it easier to see what's going on. So what's going on is you'll notice that the surface above is, the surface is directly above the domain. Okay, and so for every point x, y in that domain, every x, y, you'll see there's a point on that surface. Okay, and as soon as we step outside that domain, maybe go a little bit too far, boom, there's no point on the surface. Maybe if I go into the little cutout, boom, there's no point on the surface here because our red point down in the domain, or our red point is not in the domain. Okay. And but then as soon as we click back in, boom, looks like we hit the surface. So the domain, if you will, is living on the XY plane, and the surface is on, above, possibly below the XY plane, but it's some curvy thing, most likely, that is exactly above the domain region in the XY plane. So let's practice with these multivariable functions. So example 1, evaluate f of xy equal to 3x squared times the square root of y minus 1 at the following. And so in A, we want to evaluate f at the point 1, 4. That is, we want to find f of 1, 4. So here, we're going to replace all the x's in the equation with the whatever's in the first coordinate, that would be 1, and we'll replace all the y's in the function with all the things in the second coordinate, namely 4. So this will be equal to 3 times 1 squared, square root of 4, minus 1. There's the yellow x and the blue 4. So what is this? This looks like 3 times 2, which is 6 minus 1, or 5. So notice here what we're saying is that the point 1, 4, 5 is on the surface, or the graph. The next question asks us, what is the domain of this function? And asks if we can graph it. So we're going to look back at the original function, and just like we did in pre-calculus, we're going to ask ourselves, are there any places where f of xy equal to 3x squared root y minus 1? We're going to ask, is there anywhere where this would be undefined? And the thing that should come immediately to mind is there's this square root showing up. And we know that you cannot have a negative number under the square root. So that seems to be the only possible issue. And so to find the domain, we need to look for where the thing underneath the radical, the radicand, y, is greater than or equal to 0. So this would be our domain for the function. If we wanted to graph this, notice we have, that's the ugliest x ever. We have x and we have y, and we're saying that our domain is all the y's greater than equal to 0. So that would be from the from the x-axis on up. So here would be our domain of f. Example 2. Sketch the domain of the following functions. A, f of xy equals the ln of x squared minus y. Here, our domain is going to be dictated by the ln function, and you'll remember that the ln function likes only positive numbers. It doesn't like negatives, it doesn't like 0 either. And so our domain here is going to be where the argument of the ln function, x squared minus y, is greater than 0. Because again, this will make the ln happy. So we could solve, and this tells us that x squared is greater than y, or if you will, y is less than x squared. So if we wanted to graph this, again, we have our xy axes. And it looks like we need to graph the boundary when y equals x squared, but we don't want to include it, so we'll make it nice and dashy. So this is the line y equals x squared. And then we know we're going to have to shade above this or below this. I'm a big fan of test values. I just don't like to be wrong on things that I don't have to be wrong about. So I'm going to test with a point that's not on the graph. So maybe I'll test with the point, how about 0, 1? So that's this point right here, 0, 1. And if I put in 0, 1, I would get 1 is less than 0 squared. True or false? This is false. That tells me that everything on the side with the test point is false. And so my shaded region should be the area below the quadratic. You don't have to do test values. I'm just saying that I tend to like them myself because they give me confidence that I know which side of the graph to shade. Once again, we're using the dashed line on y equals x squared because of the fact that we have the strict inequality. So that's why we have the dashed line. In part B, we're asked to find the domain of f of x, y, z equal to the square root of 1 minus x squared minus y squared minus z squared. So here again, we see that the factor influencing our domain is that square root, and square roots like only non-negative numbers, that is, things that are positive or equal to 0. So our domain here will be the argument 1 minus x squared minus y squared minus z squared. And we want that argument, that radicand, to be bigger than or equal to 0. Or in other words, we want 1 to be bigger than or equal to x squared plus y squared plus z squared. In this case, I want you to notice that 1 equal to x squared plus y squared plus z squared is a sphere with radius 1. And then it's centered at the origin. Centered at the origin. So with that in mind, we want to have our radius in our domain be at biggest 1. And so our domain is going to look like a sphere. Okay, with radius 1. This is x. This is y. This is z. And our ball has domain 1. Maybe this is not to scale. And specifically, because of the inequality that we are given, so notice there's this inequality that 1 is greater than or equal to 1. Then this ball that we have drawn here is a solid. Whoa, that didn't work. Is a solid. So if you think about the types of balls that are out there, say in sports, you have tennis balls, baseball, soccer, pool, like a pool ball, football, like lots of balls. Well, this isn't like a football because it's the wrong shape. It isn't like a tennis ball because a tennis ball is hollow. Similarly, a soccer ball is hollow. This one is sort of like a baseball or a pool ball in the sense those are both examples of spheres that are solids, right? So it's filled all the way in, all the way to the core of the ball. Graph of multivariable functions. Recall that for a function f of one variable, the graph of f of x was defined to be the collection of all the points x, y, where y equaled f of x. Similarly, the graph of f of x, y is defined to be the collection of all the points x, y, z, where z equals f of x, y. Previous examples we've seen of this include planes and quadric surfaces in 3 dimensions. But notice this does not include lines. Not lines. They're not lines because of the fact that lines would be only a function of one variable. That parameter, oftentimes we use t. So planes, yes. Quadric surfaces, yes. Lines, no. Definition. If f is a function of 2 variables with domain D, then the graph of f is the set of all points x, y, z in R3 such that z equals f of xy and xy is in D. And we've already had at least one example earlier that we mentioned, but here we're going to show a few more. Example 3. Sketch f of xy equals negative square root of x squared plus y squared. This is kind of interesting. So this is like sketching z equal to f of xy equal to negative square root of x squared plus y squared. That's a little bit hard on my brain. So since it's hard on my brain, I sort of visualize it in a couple ways. I ask, what would happen if x was equal to 0? See if that helps me see what happens. In that case, I would have z equals negative square root of 0 plus y squared. And I hope you remember that the square root of y squared is the absolute value of y, specifically negative. And so if we had our axes in 3 dimensions, so here's y, x, and z, then this would be an upside down absolute value function in the zy plane. So it would be a cone, or sorry, a cone, like an upside down v. And similarly, if x was equal to 0, then I would have z equals negative the square root of, sorry, this is x equals 0 twice. I mean y equals 0. I'd have z equals negative square root of x squared, or negative absolute value of x. And so that would be kind of coming the other direction, also an upside down v. And then I think about the x squared plus y squared. Where have I seen that? I've seen that in the context of circles. And so what I want you to see is that this thing is equal to an upside down cone. Oftentimes when I'm sketching, I sort of sketch a chicken scratch graph like this, and then I graph a new sketch that shows that's a little bit prettier, letting everything come together. And so I've got a cone, it's upside down, and then maybe I can add my axes. I know that the z is going up, coming down, and I know that the tip of the cone is right at the origin. So here's my y, and here's my x. So there is my sketch of this surface right here that we've shown. This surface is f of x, y. Sketching surfaces like this is challenging. Technology is definitely your friend. Wolfram Alpha and many other function or graphing apps can help you to generate some of these graphs. The surfaces we studied previously are easy, quote unquote, to graph by hand, but many others are not. There are computer programs that are capable of graphing functions of two variables. We call these surfaces in 3D. In most programs, traces in the vertical planes x equals k and y equals k are drawn for equally spaced values of k. Let's see if we can see that in the picture. So notice here in this first picture that if you follow along the curves in the picture, these would each be for an equally spaced. Notice they're all like parallel to the y-axis. So these would all be for various y equal k values. And then likewise, you could come along the other direction. You can see the graphs, the pictures in the line, and those would all be parallel to the y-axis or where x equals k. And so these lines are all examples. These lines are examples of what we call traces. So you can imagine you set y equals to k and you figure out what's the curve, like what's the line, like we talked about back in chapter 13 with the space curve. So it's the equation of those space curves. And so you graph a whole bunch of those space curves and kind of the web of them forms the surface. Let's look at another example. Here, once again, you have the traces with y equals k, and then we could also have the traces with x equals k. And these need to be equally spaced along the x-axis and along the y-axis in order for this to look right. At the end of the day, using technology, we can make some pretty amazing looking graphs. These are just a few. And when you add rotation to the mix, I really do think this is one of the most beautiful classes that we have to offer at Highline College. Step aside art, we've got math. Or maybe we should do them together. I guess that's why we call it STEAM instead of just STEM. Science, technology, engineering, art, and math. So these figures are an example of computer-generated graphs. I believe all these were made with Mathematica. Note that A and B, so this would be A and B, this guy and this guy. This is the same function, but from two different perspectives. We took that graph and then we twisted it. And so you could see the two towers pretty clearly in A, but in B, they were twisted. And so one is sort of in front of the other. And so it's a little harder to see what's going on. You can see that the graph is becoming flat as you move away. So here, It's flat as you move away from the origin. Notice how it just gets flat here, kind of on the boundaries. Okay, and this is because that graph of e to the negative x squared minus y squared approaches 0, aka the xy plane, as x and or y become infinitely large. Level curves. Functions of two variables can be represented as surfaces, like we saw in the previous example, and can be described in two dimensions by contour maps and horizontal traces, which are all called level curves. Definition. The level curves of a function f of two variables are the curves with equations f of xy equals k, where k is a constant that is in the range of f. So a level curve f of xy equals k is the set of all points in the domain of f at which f takes on a given value k. In other words, it shows where the graph of f has height k. In the picture, you can see the relation between the level curves and horizontal traces. The level curve f of xy equal to k, these are just the traces of the graph of f in the horizontal plane, z equals k, projected down onto the xy plane. So if you draw the level curves of a function and visualize them being lifted up to the surface at the indicated heights, then you can mentally piece together a picture of the graph. The surface is steep where the level curves are close together. It is somewhat flatter where they are farther apart. Note, a graph made up of level curves is called a contour plot. Outside of math, perhaps you've seen a topographical map. This is roughly the same thing. I also want to point out an important detail, namely that when constructing a contour plot, the level curves should be equally spaced. For example, you could have k equals -4, 0, 4, 8, 12, 16. In this case, each time k is going up by 4. They're spaced 4 apart. Or you could have k equals 1,000, 1,050, 1,100, 1,150, where the k's are 50 apart. Or in the picture that's given, notice there are k's, there's 45, 40, 35, 30, 20. So you get k equals 20, 25, 30, 35, 40, 45. All of our k's are 5 apart. So the k's are supposed to be equally spaced. Rather than spending a lot of time on this picture, I have a number of animations or manipulates that help you to visualize and understand what's going on with contour plots. So here's an example where you can see what's going on with a contour plot. So notice that we have this kind of mountain-shaped object, and we're slicing it with a horizontal plane at the height of z naught. Okay. You'll notice that we could look at equally spaced z values. So let's see what they are. We've got 0.4, 0.6, 0.8, 1, 1.2. So each of these is 0.2 apart. And we look at the shape of the curve, like that darker green line, where the plane intersects the little mountain. And we take that shape and we graph it on the XY plane. And you can see over here on the right, you'll see the level curves, or the contour plot. So again, each time we change those z values, we're going to get a different ellipse. One thing I want to point out, that I also want to point out here, is that, come on, little buddy, that the level curves are farther apart. They're farther apart down here at the base. Let's change the color, this matches. So down here at the base, they're farther apart and getting farther apart. And notice that's where the graph is flatter. And then they get close together, this would be where the graph is steepest, kind of here in the middle. And then notice right at the top, they're actually getting farther apart again. This is where the graph flattens out here at the peak. Okay. That round spot, like the little circle, whenever you see a circle on a contour plot or a topographical map, it either means you're at the top, like the top of a mountain or a hill, or maybe you're at the very bottom, like a hole. The contour plots would mean the same thing unless we had more information to tell us which was which. So here, another example. Okay, so it looks like we have kind of this funky, I don't know, like ridge type of shape, if you will. And let's see, does this one jump? Yeah, it does. Nice. Oh no, not quite as nice as I was hoping. So notice we have a line. Come on, little buddy. We have a line at -3. And then we don't show any of these middle lines, but we show the line at -2. We don't show the intermediate lines, but we show the line at -1. Again, we're showing all these lines because the ones we're showing because we want to make sure that we're only showing lines that are equally spaced. So contour curves are formed by the intersection, in this case of the surface z equals y minus x squared minus 1, and the planes z equals z naught, or z equals k. So here you have those level curves. Oftentimes we will draw this surface, we'll draw this contour plot or these level curves because it's much easier to draw things in 2 dimensions than in 3 dimensions. Let's look at another example. This example is similar to one of the earlier examples with a couple of notable details. One, notice that it looks like we have actual circles. In the previous example, we had ellipses. So you have circles. Once again, the circles are getting farther apart at the outside, which is representative of the fact that our surface is getting flatter here. And then also note you have the nice circle at the top. It's reminding us that basically at the top, everything is the same height. That is pretty flat here, right at the peak of our little hill. So here, contour curves are formed by the intersection of the surface z equals -x squared minus y squared, and the planes z equals z naught, or z equals k, for 0 less than z naught less than or equal to k. And we can once again see how those are formed. So see, if we notice that they're all equally spaced again, 0.8, 6, 0.4. I feel like I keep repeating that, and the reason is because one of the most common mistakes students make when constructing contour plots or topographical maps is simply that they don't equally space their z values. Two more examples. What I like about this particular example is notice that for any single z value, notice that there are an infinite number of times when the graph is going to achieve that. So it looks like we're gonna hit it here, we're gonna hit it here, we're gonna hit it here, and presumably it looks like here, probably up here. And those are all parallel to each other. And so the parallelness of the contour plot is because our surface is almost like a sheet of paper. It's like a wave where you have all these parallel lines. It's going to create kind of a waviness. Notice the contour plot has a hard time telling us where things are going up and where things are going down. It just tells us kind of the steepness. And so you can see that in this region, the contour lines are close together, so it's going to be steeper. That's going to be these parts in here, like in the middle. And then in other places, you can see the contour plots are farther apart. Right? Notice the difference here, that's this distance apart, but you also have this distance, right? These are the very, very flat parts. And so maybe that's this base, or kind of like the peak here where it's pretty flat, could also be at the base where it's very flat. So this flat spot here might represent a high spot. The next flat or kind of big gap might represent a low spot. But as soon as you see those long parallel lines like that, all these parallel lines, that tells you have this nice wave happening, like a folded sheet of paper. It could be the paper is going like this. It could even be that the paper is a plane. We'll talk more about that possibility later. This is the last example of a contour plot that I want to show at this time. This is the level curves of electric potential functions. And I'm not a physicist, so I'll leave it to the physicists to do the fancy interpretations. But you can sort of see the two poles, I believe. And what I want to point out here is that there's this region where our curve is cutting through, and it's actually slicing twice. You have a little circle here and a little circle there, representing the two different peaks. And kind of a fun thing happens. You get down to the certain point, it's getting a little less steep, but you get to this fun point where there's actually like this figure 8 thing that's happening. Come on, little buddy, you can do it. Oops, I got too carried away. Go back. Oh, too far. Back. Okay. So what are we saying here? What we're saying is that, and I think this is an important point, is that if you were a person and you were walking along this curve, you could walk around both, like we could just take this path and we would never change heights as we walked around that path. It's a level curve. It doesn't change any heights. If you came down, if we were to walk around this curve going around the mountains, which one is that? That's this one here. We would never change heights as we came around the mountain. It'd be the same level height. So if you want to not change heights, like stay at the same altitude, you would stay on the level curve. If you wanted to go really steep, so along the level curve would be the same height, but if you want to be really steep, then you would go perpendicular to the level curve, right? And perpendicular to the level curve will send you straight up the mountain, so to speak, okay? From whatever point you happen to be starting. So I hope you have a little bit of a picture of level curves, what they look like, and kind of how to work with them. Example 4. Recall the function in a previous example, f of xy equals negative the square root of x squared plus y squared. What are the level curves? Sketch them for a few values. We already saw the picture. The picture is of an upside down cone. Let's see what this looks like with level curves. And so we're going to choose some different values of z equals k. We get to choose. It's our choice. So we're going to choose. So maybe I'll choose z equals 5, z equals 0, z equals -5, z equals -10, z equals -15. And I chose the negatives because I knew from our previous work what was going to happen, at least roughly. So I wanted to set myself up for success. But I made sure to choose at least one positive so that you could see what happened there. So if we look at our positive 5 to start with. So I want to graph 5 equals negative the square root of x squared plus y squared. Now notice the square root is always going to be positive, so negative the square root is always going to be negative, and so this has no solution. Let's look when z equals 0. So here we're going to be graphing 0 equals the square root, negative the square root of x squared plus y squared. And this would only have a solution when xy equals 0, 0, like right at the origin. Okay. How about if we looked at negative 5? So if we said negative 5 equals negative square root of x squared plus y squared. Well, you've got a negative on both sides, so that can work. If we squared both sides to get rid of the radical, this tells us that 25 would equal x squared plus y squared. Wait, what is that? That's a circle centered at the origin with radius 5. Okay. If we were at z equals negative 10, we'd have negative 10 equals negative square root of x squared plus y squared. You can sort of see what happens. This would be 100 equals x squared plus y squared, which is a circle centered at the origin with radius 10. And I think by now you're catching the pattern. Z equals negative 15 would be 15 squared, or 225, equals x squared plus y squared, which would be a circle centered at the origin with radius 15. So if we wanted to graph all of this, we would, I guess I'm going to go off to the side here. So we would have our axes, x and y, and it looks like we want to have concentric circles. So we know right at the origin, there's just a point, and then we're going to come through here at 5, and then come back around, same distance apart at 10, and then come back around at 15, and et cetera, et cetera, et cetera. Oh, and the first one was at 0. So here would be our contour plot. Contour plot for f of x, y equal to negative square root x squared plus y squared. Last concept in this section, level surfaces. The concept of a level curve for a function of 2 variables can be extended to functions of 3 variables. If k is a constant, then an equation of the form f of xyz equals k, notice that, again, k is a constant, will, in general, represent a surface in 3D. The graph of this surface is called the level surface with constant k for the function f. They are generally more difficult to visualize than functions of 2 variables, but every now and then can be really advantageous for us. Example 5, describe the level surfaces of the following functions. A, f of xyz equals x squared plus y squared plus z squared. So what I tend to do is I tend to set some values. So if I let k equal 1, then this would be 1 equals x squared plus y squared plus z squared. And I see that and I say, this is a sphere. Then I'll come in here, maybe I'll let k equal 2. And I get 2 equals x squared plus y squared plus z squared. This is also a sphere, and so I got to ask myself, how are the spheres different? Well, the second sphere has a radius of square root of 2, and it's centered at the origin. The first one has a radius of 1, and it too is centered at the origin. So I'm getting a feel for what's going on. So let's continue on and look at a couple other values. So if I let k equal 3, I would get 3 equals x squared plus y squared. Notice I'm keeping my k's equally spaced. And I look at this and I'm like, this is also a sphere with radius square root of 3. And do one more. If I let k equal 4, I'm going to get 4 equals x squared plus y squared plus z squared. This is also a sphere. This one has radius 2, and it's centered at the origin. So the question asked me to describe the level surfaces of the following functions. So here we would say that the level surfaces are spheres with radius square root of k centered at the origin. All right, so here we can see this graphed, and notice that we have a little sphere on the inside there. Then we have a bigger sphere, okay, which is here, and then we have an outer sphere as well. And one thing I don't like about this particular example is that you have the nice looking picture, but notice that in this very nice looking picture, it lines up with k equals 1, k equals 4, k equals 9. And so in this particular example, the graph emphasizes the prettiness of the picture, but does not have the equally spaced k values that I think are pretty important in understanding what's going on when you have contour plots, or in this case, the level surfaces. B, f of x, y, z equals z squared minus x squared minus y squared. So here we're gonna just choose some values again. So say I try k equals, I don't know, 4. Try 4 because there's a whole bunch of squares, so at least the numbers might make sense. So I have 4 equals z squared minus x squared minus y squared. And so what I notice here is that if I let z equal, if z was 0, then I would have 4 equals negative x squared minus y squared. That can't happen. So z equals 0 doesn't work. How about z equals 1? So in this case, I'd have 4 equals 1 minus x squared minus y squared, or move the 1 across, 3 equals a negative. That can't work. Well, I think you can probably see that z equals 2 would work. Because if z equals 2, I'd have 4 equals 4. Okay, that could work. And z equals 3, that could work as well. So if you plot these things, you will see that this is the hyperboloid of 2 sheets. Something like that, which we talked about back in the section on quadric surfaces. In this case, it looks like we're going to have the bottom of our upper sheet at 2, and the top of our lower sheet at -2. So this is a hyperboloid of 2 sheets. And I think you could go back to section 12.6 on quadric surfaces if you wanted a review of this particular topic. So then we let k equal 0. So notice I went down by 4. And so now I've got 0 equals z squared minus x squared minus y squared. And I'm hoping that you recognize this is the cone that we had earlier on in the section. So this is our cone. Something like that. So it's a cone. It's a cone that has both a top and a bottom part. And if we keep on going, again, we're going down by 4. So maybe I let k equal -4. So now I have -4 equals z squared minus x squared minus y squared. And I notice that if I let z equal 0, I have, so z equals 0, that would give me -4 equals -x squared minus y squared, or 4 equals x squared minus y squared or plus y squared, which is a circle with radius 2. We know what this is. This is a hyperboloid of 1 sheet, like the old cooling tower. Hyperboloid of 1 sheet. Come on. And we can see that below in the picture. So we did our work. You can see that when k was equal to 4, that's bigger than 0. That's where we have the 2-sheeter. When k was equal to 0, that's where we have the cone. And when k was equal to -4, that's where we have the hyperboloid of 1 sheet. And the crazy part is that all of those hyperboloids are level surfaces of the same, like, 4-dimensional object, whatever that means. Again, the one final note, just to repeat on A, in the spherical example, the values of k pictured are not equally spaced. Before we conclude this section, I would like to show one more animation of this, just so that you can get another picture just with the fancier technology generated curves. So here we are looking for level surfaces of w equal to f of xyz equal to the square root of z minus x squared minus 2y squared. Here's our surface. And notice that each of these level surfaces is a full shape. So when w equals 0, so if I had 0 equals square root of z minus x squared minus 2y squared, I'd get this shape. If I had w equals 1, I'd get a shape but just a teensy bit inside the first one. W equals 2, also inside, but a little bigger gap there. And w equals 3, you get just a little teeny cap right there on the middle. So you can imagine that as we go farther, we would get kind of the smaller things, or maybe they just shoot up farther. So that gives you some sort of a sense of what those level surfaces are. They're saying, fix this value for w, and then what is the surface that results. So there you have this lesson on basically curve sketching in 3 dimensions with level curves and functions of more than one variable. This is just one short lesson. We're not expecting you to understand everything and all the intricacies, but we hope that it gives you an idea of what's going on, what's to come, as we are about to dive into something absolutely beautiful and also not very difficult, namely the partial derivative. So thanks very much, everyone, and I will see you next time for partial derivatives.